go. So I'm slowly learning that the video camera can't hear anything really unless I'm on the mic. So we'll go that way today for the video. All right, thank you all for joining us for our second seminar of the fall season here. We've got a couple of announcements and we're going to try the introduction thing again. So, have anyone new they would like to introduce today? I have one. So my group has a visiting scientist from China, Tony, right here. And Tony came in August and is here until January and is over in the Forest Suite in Ag Science North. He hails from Fujian province and is an associate professor at Fujian Normal University, and he's a forest ecosystem ecologist by training. So there's one. No one else. Oh, Erin.
I'll introduce somebody. I'll introduce Christy Durbin. So Christy's the CSA manager at the South Farm, but she's also starting as a graduate student in the PSS program this semester. Okay.
Correct. Welcome, Christy. Anyone else? Okay, very good. We have one announcement, two announcements. Our next seminar speaker, I believe, is Art, right? So next week, come and listen to polyventilation updates. And then the IPSS Graduate Student Association would like for me to announce that they are trying to form a sand volleyball team to play at Eureka's on Friday evenings at D-League, which is purely recreational and not competitive. 6 weeks of games, they start in October. They're between 6:30 and 9:10 each week, and they last about 40 minutes. If you're interested in playing, you can talk to Rebecca McGrail right here in front, I believe. And faculty are invited, so I think this is an open. So Randy, I know knees and back are good. You're ready to go, right? All right. Okay, well, today it's my pleasure to introduce Dr. Bill Haneberg, who's the director of the Kentucky Geologic Survey. And he provided me with a nice little bio, so I'm just going to use that today. He's the state geologist and the director of KJHS, and he has a faculty appointment as a research professor in the Department of Earth and Environmental Sciences here at UK. His expertise includes digital terrain modeling and geologic characterization using high-resolution topographic and bathymetric data, computational geology and GIS applications, geomechanics, and geohazard and risk assessment. Before moving to Kentucky in 2016, he spent 17 years as a consulting geologist, first as a sole practitioner based mainly in Seattle, and then with Virgo in Houston, Texas, where he led a team of geologists, geophysicists, and engineers working on quantitative geohazard and risk assessments for deep water oil and gas projects around the world. He spent 11 years at the New Mexico Institute of Mining and Technology, rising to the position of Senior Engineering Geologist and Assistant Director of the New Mexico Bureau of Mines and Mineral Resources, before he left to establish his consulting practice. He's authored a ton of papers and abstracts. He's been a co-editor of a couple of monographs and has won several awards in these areas as well. He was the 2011 Richard Hahn Distinguished Lecturer in Engineering Geology and has held adjunct faculty positions at New Mexico Tech, Portland State, and the University of Cincinnati. He earned a BS in Geology from Bowling Green State University. Do you actually hail from Kentucky?
Oh, no, Bowling Green, Ohio.
Oh, I'm
yeah,
sorry.
the real Bowling Green.
I'm showing my own preference there. So he earned a BS in Geology from Bowling Green State University in 1982. And his MS and PhD in geology just up the road at the University of Cincinnati. So join me in welcoming Bill.
Thank you. So, yeah, I actually
We have several of those in the crowd today, I think.
Well, thank you all for coming out today. I was just thinking, one of the things I really enjoy being back in an academic setting after 17 years in industry is really the wealth of opportunities just for continuing professional development and education seminars like these. So yesterday afternoon I was at a seminar about cave systems and groundwater flow in the Grand Canyon. I'm actually missing our weekly KJHS seminar right now, which is about Oligocene age catastrophic rock avalanches in Nevada. And I'm here today to talk to you about the Kentucky Geological Survey. And that, I think, it's one of the most amazing things about being in a big research university. It's almost, no matter what field you're interested in, you can find something to do almost every day of the week in the way of enrichment and continuing development and learning opportunities. So Rebecca asked me a while back if I would give just a general talk about the Kentucky Geological Survey. Just to have a show of hands, how many people have heard of the Kentucky Geological Survey? So most of you have, so that's good. What I want to do today, and what I did is I shamelessly stole the PowerPoint presentation that we have running in our atrium lobby for people to, because it's a good overview of what we do in terms of groundwater mapping and terrain modeling and things like that, and I've annotated it and expanded a little bit. So I'll give you a really broad overview about what we do, maybe enough to get you a little bit interested in one or two of these topics, and of course you're welcome to ask questions later, we can follow up on that. But this was our staff. Actually, it was in the first week that I started here about 2 years ago, in 2016. So I've been here almost exactly 2 years, September 1st, 2016. And the line at the bottom is our vision, which is to be the primary source of geological information for and about Kentucky. So our goal is, if you think about anything related to geology in Kentucky, whether it's sinkholes or groundwater or landslides or oil and gas or coal, the first thing that's going to come to your mind is, I need to call KJHS. I need to email KJHS and ask them about this. So we actually have pretty deep roots in Kentucky. We go back to 1838, and interestingly enough, when you realize the histories of KJHS, the first geological survey or geological reconnaissance of Kentucky took place in 1838 and 1839 by Williams Mather. It was actually the descendant of the famous Mather Puritan family in Kentucky, who was behind the witch trials in Massachusetts. But one of his descendants was an artillery instructor, chemist, and professor who had gone to West Point and became one of the early North American geologists. And according to some of the histories, and I think even one of the terms that was used was a group of agricultural agitators. And I have a hard idea of picturing what exactly those were, but apparently a group of concerned farmers went to the legislature and said, we need a survey of the resources of Kentucky. And you can imagine what Kentucky was like back around 1830, 1835, 1838. There was a lot that wasn't known. So the legislator allocated $1,000, a ransom of $1,000, and told the governor to appoint some competent person to conduct a geological reconnaissance of Kentucky. That was Williams Mather, who's shown in the slide there. So he completed the first survey, turned it in. He recommended, or first reconnaissance, sort of subtle distinction, but he recommended that what you really need is a more comprehensive, true geological survey of the state. He did a really quick 1-year tour of the state and wrote some things up. It was really good work for what he did, but he said, yeah, you need to actually undertake a serious survey. And a number of years passed, and in 1854, the first comprehensive survey, geological survey of Kentucky, was undertaken by a famous geologist for his time named David Dale Owen. The Kentucky Geological Survey has existed in fits and starts, often during wars. It was sort of abandoned and dissolved, and there were a few political arguments here and there. It was shifted from agency to agency, and there were a number of years here and there where it didn't exist at all. But the modern Kentucky Geological Survey, as part of UK, dates back to 1948, when it was actually created. So it's in KRS, you can see down there, 151.03. So section 151 defines the Kentucky Geological Survey and said it will be part of the University of Kentucky, and it outlined who can be employed, and that there will be a state geologist selected, and so on and so forth. But in terms of what we're supposed to be doing, it's a mission that's very broad and very general, which can be either good or bad, depending on how things are going. But it basically says the Kentucky Geological Survey shall make the continuing geological study of the state and perform other such functions as are directed towards the development of mineral resources in the state. In a good year, you might not get too much direction, and you can pick out what you want to work on and do productive work. But that's basically our charge, to conduct a continuing geological survey of the state of Kentucky. So right now we have, give or take, about 50 FTE people. We add up things like student employees, so sometimes that FTE fluctuates up or down, but it's about 50 people. Our main offices and labs are in Mining and Mineral Resources Building down on Road Street. We also have a well sample and core library. I'll talk a little bit about that later. Out in the research park near CAER, so that is a large warehouse containing core samples and cuttings from different kinds of wells in Kentucky. We have a Western Kentucky office in Henderson that does a lot of work with the College of Agriculture people. And then within the survey, we have 5 technical sections. So we have water resources, we have geological mapping, we have energy and minerals, and we have geological hazards and geologic information. And quite a few of our UK or KJHS scientists have adjunct appointments, mostly in the Department of Earth and Environmental Sciences, one is in geography, and then I have a research faculty appointment in ES as well. So what are some of the things we work on? Well, one is water supply. We don't want to ever try to compete with private consultants, but we do a lot of work just in terms like aquifer definition, aquifer delineation, sometimes helping nonprofit groups, government agencies select sites for water supply wells. So water supply has always been an important part of our work, especially in the water resources section. We do a lot with water quality. We have a water quality lab here on campus. We do quite a bit of sampling and analysis, especially for domestic wells. We're doing a lot of work with ag people, and right now we have several projects going on with Brad Lee on edge of field water quality monitoring in Western Kentucky. So this is when back from our staff. They're installing flumes at the edge of the fields and collecting runoff after rainfall events and then analyzing those. I think that's a 5-year study with a potential for extension to 10 years in several locations throughout Western Kentucky. So we're very active in that. And this is Mark Ackman from the park here who's actually working out of our Henderson office with one of those projects. We also operate the Kentucky Groundwater Observation Network. This is a map that has a lot of things on it, but it actually has the green and purple and yellow triangles represent the green ones are the continuous monitoring wells that are part of the Kentucky monitoring network that we operate. It's basically using existing wells. We've been building new wells for this. The purple ones are anticipated wells or wells that we periodically monitor. We have some Carson monitoring sites. I guess I had a different version map that show wells we had considered or rejected. But basically, we're responsible for running the monitoring network and coordinating an interagency groundwater monitoring report that comes out once a year that's submitted to the state. So that's sort of one of our mandated functions. We're the official repository for groundwater information within the state, coordinate the interagency groundwater monitoring project. If anybody wants to drill oil or gas well in Kentucky, they have to submit a permit application. And that comes to us and we look at it and say, hey, we need samples from when they're drilling. So we specify which depth ranges or which formations, and we curate those samples. So we have several mandated sort of data collection and archiving functions in addition to just doing research throughout the state. Sinkholes. Sinkholes are always a popular topic, at least in some parts of Kentucky. We've had people working on sinkholes for decades now. We just this past spring or June hired a new Carson hydrogeologist from, of all places, the Grand Canyon. Decided Kentucky is a preferable place to work on Carson to the Grand Canyon. Even though it is quite a scenic, he actually insists that the Carson cave systems are much better here. So we've been doing Carson sinkhole studies for many years. I'll show you some examples later. One of the really neat things we're doing now is using airborne LiDAR to map sinkholes that would otherwise have gone undetected. And we are just now, I'm trying to think if it's actually on the website and published. If it isn't, it will be imminently a technical paper on cover collapse karst looking at the damage, which amounts to tens of millions of dollars a year in Kentucky just from these surprise events. We walk out and all of a sudden there's a huge hole. And if you're lucky, it's in your backyard and you're not like some of these people you hear about, like the guy who was asleep in bed one night and just bottom of his house literally dropped out. So karst is a big concern. You all know about things like the Corvette Museum. Most of the failures aren't as big and spectacular as that, but they do add up when you integrate them over the entire state. And we have karst potential maps. You can see the dark blue areas especially are the highest, the middle, medium blue areas are lowest, or medium, and then the whitish areas are the lowest karst potential. So we range from the synoptic statewide studies where we come up with a map of something like karst potential or landslide potential for the entire state, and then can zoom in and do very detailed site-specific studies. Karst conduit research, especially things like dye tracer studies. Jim Currens, who worked for us for several decades, retired a little over a year ago, and we're still wrapping up the publication of some of his map of decades of basically tracer studies looking at karst flow patterns. If you don't dye in a sinkhole one place, where does it come out? And it turns out that's an incredibly complicated problem. And the less data you have, the simpler it is, but as you get more data, you find out you may dump it in this in one sinkhole and they come out in 2 or 3 or 4 different springs in totally different directions. So it's like trying to unravel this puzzle of the surfaces around that you never quite understand. But we've been active in this kind of work for many decades. We do a lot of energy research. Back in the 70s, a lot of that was driven by coal and to a lesser extent oil. It's an interesting time to be in Kentucky when you look at the evolution of the coal industry, both for environmental and economic reasons. It turns out of all the places you could mine coal, Eastern Kentucky is also a very difficult, technologically difficult and expensive place to mine coal. So we're in many ways an organization that's changing. We have a lot of people that work for us for 30 and 40 years who were hired as coal geologists, but the environment has changed, the economic situation has changed over the decades. But we still do a lot of energy research. Some of these photos are from the Berea Sandstone Consortium. The Berea Sandstone is a fairly productive oil and gas reservoir in Eastern Kentucky. We had an industry government consortium for several years. We did some collaborative work with them. It's just showing the field trip and examination of some of the cores. But part of this is also we are the repository for oil and gas drilling data from Kentucky. Coal resources. We still have people who go underground, and if you walk around the mining mineral resources building, sometimes you'll see a person and completely covered in black from head to toe, and so maybe with the goggles and the face masks were. So we do a lot of quantifying Kentucky's coal resources. And the interesting thing is, even if we stop burning coal, there are other uses of coal. So there's thermal coal, which you burn for heat, or steam coal, it's sometimes called. But there's also metallurgical coal. Basically, you can't make steel without carbon, and you get the carbon from the coal. So there's some kinds of coal that are very useful for making coke to make the carbon put into the steel. One of the really exciting lines of research we're collaborating with people at CAR and the mining engineering department here in the UK is rare earth elements. That coals contain unusually high proportions of rare earth elements. So the big question is, can we extract them? And I don't know if any of you follow the whole strategic mineral scene, but if you look at the sources of a lot of strategic minerals and especially rare earth elements, there are places like China or Afghanistan is like this treasure trove of really valuable things, but not a lot of people want to go and mine in remote regions of Afghanistan. So one of the things we're looking at in collaboration with the mining engineers and people at CAR is extraction of rare earth elements from coal, both from coal combustion products and actual coal, things like dust that you wash off of coal when you're processing it. So one of the big questions would be, well, okay, what happens if the emphasis or interest in coal shifts from thermal properties to rare earth elements? For decades, we've been trying to characterize sort of the thermal properties of coal, but we don't know that much about the distribution of rare earth elements. So that might be a really interesting problem to work on into the future. We worked on carbon capture and storage as part of some regional consortium, funded in part by the DOE, in part by the state of Kentucky. We drilled a couple of deep wells, including one 8,000-foot deep well in western Kentucky. So that provides, in addition to characterization of the rocks to try to determine if they're adequate and have the proper seals to use for carbon storage. If you adopt a carbon capture and storage scheme, you have to store it someplace. One of the issues is that the earth is sort of leaky. In fact, that's one of the ways we actually explore for oil and gas is look for seeps coming up out of the seafloor. So we know the earth is leaky, but it has some sealing properties because it can accumulate oil and gas on its own. So the question is, if you're going to do carbon injection, carbon capture, and try to store it in the subsurface, where do you go? What are the best rocks to store it in? So we've been involved in a number of those projects, working with other state surveys and US DOE and groups like the Tel Labs and Columbus, trying to understand what the capacity of rocks, especially in Kentucky, might be for carbon storage and sequestration. Tar sands. We have some tar sands in western Kentucky. They're not quite economic. Years and years ago, they were actually mined and used for paving materials. This was sort of like already made asphalt. You just dug it up and tamped it down and made a road. But they were out there, so we evaluated those, and they don't look economic at this present time, but it is sort of an interesting curiosity about western Kentucky. Strategic minerals, I talked a little about that in terms of coal. In the far western Kentucky, there are some heavily faulted areas that have accumulations of minerals like fluoride, which is calcium fluoride, that can be very useful, can be very important. It turns out right now the fluoride market is such that they're not really economic, but we do have some things that qualify as strategic minerals in far western Kentucky. We took in just about a year and a half ago many thousands of feet of core samples to some fluoride projects in western Kentucky, so we have those available just to characterize the deposit and potentially came to that provide information to supply the economics. But one of the interesting things is if you look at these maps, all of the black lines are faults in western Kentucky. The purple areas are fluoride accumulations. So you can see it's pretty well controlled by hydrothermal fluid flow along these fault zones. So key to understanding where the deposits are is going to be understanding the geology, understanding the network of faults and the stratigraphy of the layer of rocks in order to better anticipate where the best deposits might be and if they're mineable, how to mine them. Industrial minerals, they're sometimes don't seem as glamorous as other things, but you're talking about like aggregates for construction, sand and gravel. If you think about it though, if you don't have sand and gravel, or if you have to bring in sand and gravel from hundreds of miles away, like they do in some areas, it can be a real burden on the economy. Agriculture, rock dust for coal mines, limestone. We have a lot of limestone in Kentucky, and it seems over time we periodically get requests from people who are interested in, especially, say, pure forms of calcite used for industrial processes or chemical processes. So we do what we can to keep track of industrial minerals and just released and put online even down to the field notes of one of our geologists who spent several decades studying limestones in Kentucky. So they're incredibly detailed side-by-side descriptions. So even things that are seemingly run-of-the-mill and mundane as limestone or sand and gravel can be economically very important. We do a lot of geological mapping. Not a lot of people know this, but Kentucky was the first state to be mapped in its entirety from border to border with modern detailed geological maps. And that dates back to about 1960 when the state of Kentucky went into joint a collaboration with the U.S. Geological Survey, and they said, and they were motivated mostly by resources, especially things like coal and oil and gas. We're going to map the entire state of Kentucky at an unprecedented level of detail. And that took over a period of 18 years, 1960 to 1978. They expended 690 person years mapping almost foot by foot, maybe more like yard by yard, the entire state of Kentucky. So that took 18 years. It took another 4 years lag time before the final paperback was actually published. And then starting back in the late 80s, early 90s, KJHS started digitizing those. They spent about another 10 years digitizing those maps. And it turns out even now, this project that was essentially completed in 1978, Ohio has complete coverage. And I think it's Connecticut or Rhode Island, one of the smaller states. But basically no other state in the entire United States has this degree of coverage. We have it all digitally and almost seamless and available for free over the internet. And people have done cost-benefit studies, and the benefit-cost ratio has been very, very high. You can argue about the methodology, about how exactly they calculated it. But it's really phenomenal to be in a state where we have complete border-to-border statewide coverage. And if you can imagine doing field work in, say, 1962 in Kentucky before all the expressways, before all the interstates, and the fact that they put in 690 person years, and they were mapped in 7.5-minute quadrangles. So there's 707 7.5-minute quadrangles in Kentucky. And they made, I think it cost $30-some million in the original dollars. And we calculated, if we were going to do that today, it would cost like $85 million. So it's an amazing investment in Kentucky. But just think if you went to the legislature now and said, hey, we want $85 million coming out of the state of Kentucky, whether or not you'd be successful. One of the collaborations that we've been developing and is going increasingly important in the past few years is geology and human health, especially working with the College of Nursing and the BREATHE program there and the College of Public Health here in the UK. And we've done some really neat things, in part because we have this complete map coverage, border-to-border map coverage. And it turns out there were about 71,000 home radon test kits available in the state of Kentucky. So we worked together with the College of Nursing people and their biostatisticians and said, well, okay, how can we combine geology and the radon results? And for example, use that to predict the radon susceptibility in areas where we had a geological map, but we didn't have any radon test results. So we came up with statistically valid distributions for each of the formations on the geological map. Technically not each of them, we want something together. But for the units on the geological maps, you can say, okay, here's the Lexington limestone. This is your min, max, mean, and 75th percentile of radon potential. And that's important because radon is the second leading cause of lung cancer. It turns out if you're in a home with radon and you're exposed to tobacco smoke, you increase your chances of lung cancer by a factor of 10. So given our high smoking rate in Kentucky, given the very high prevalence of radon, because the limestones here in Kentucky and some of the black shales are very high, have very high radon potential. And in fact, in the Lexington limestone, which gives us the bluegrass region, because of its phosphate content, the radon also comes from the high phosphate limestones because you get uranium substituting for calcite into the calcium phosphide mineral apatite, and that breaks down in radon. So the same thing that gives us all these beneficial things like bluegrass and of course the strong bones gives us radon, the second leading cause of lung cancer. So we've been working with them. We now have an interactive radon potential map on our website. We can go zoom in almost down to your street level and see whether the radon potential is high, medium, or low. One you actually see is the 75th percentile. So we find one of the interesting things now is people will say, oh, I'm in a low area, I don't have to test my house. But it turns out it's a probability distribution, so even if it's low, you still have a 25% chance it's higher than that. So we're continuing that work and starting to do a lot more in terms of proposing. We have a big NIH proposal into a citizen science program that would actually involve citizen scientists monitoring radon periodically throughout the year in their homes, looking at seasonal variations, and looking at meteorological and atmospheric conditions, and also putting radon detectors in libraries for people to check out in their own home testing. So that would be a really exciting opportunity if we proceed with that. Paleontology, everybody loves fossils, or at least most people love fossils. So we do actually have one paleontologist on staff. There's not a big commercial demand for paleontology in Kentucky. But we are doing some neat things. If any of you walk into the backside of the Mining and Mineral Resources building, you might recognize the Whitfield stump, which used to be right in front of the white classroom building. But it was excavated and moved, and over a period of about a year, they actually hired museum conservators, and they restored it and put it back into place. This is a Pennsylvania age, so it's about 300 years old, tree stump that fell out of a roof of a coal mine in eastern Kentucky in 1929. That was run by a university alumnus, and he donated it to the university, so it's now nicely restored in this, it would actually make a really neat hot tub, but they built it instead. It's like this stone circular edifice. And this is a digital model, so I think that's really neat how we can combine modern technology, like making 3D models from structure from oceanogrammetry and using that to characterize something like a 300-million-year-old tree stump. But that's right outside the back entrance to the Mining and Mineral Resources building. Be careful walking through and wonder what it is. Earthquake research. We do have earthquakes in Kentucky. The far western part of Kentucky skirts the edge of the New England seismic zone. As some of you may know, during the winter of December of 1811 through February of 1812, there were 4 earthquakes centered around New England, Missouri, which is almost within sight of the western part of Kentucky. To magnitude 7.5 and 7.3, and there was one that was an aftershock that was a near magnitude 7 earthquake. So those 4 events occurred during about a 3-month span in 1811 and 1812. So the big question now is, does this pose potential? In 1811 and 1812, there was almost nobody out there. Even now in Kentucky, it's largely agricultural. We have things like Paducah, we have the gas diffusion plant, we have things like coal ash impoundment dams, we have the entire city of Memphis right along the Mississippi River. So one of the big questions in geology now is whether or not the New England grid zone is still active. And GPS data seems to suggest it's slowing down. But we only have GPS data for 10 years. We have geologic information, especially when you can excavate and actually see liquefaction layers within the Mississippi Valley alluvium, suggesting a big earthquake like this, enough to liquefy and create huge sand blows over large areas, about every 500 years or so. So the question is, well, do we trust these GPS measurements that seem to suggest things are slowing down and maybe the system is closing up and it's not going to be active anymore? And some people say, yeah, we need to do that. It's going to stop wasting all this money on retrofitting. We're going to stop putting shear resistance that we're building in Memphis. Or you look at the geological record and say, well, wait a minute, we've had one of these like every 500 years. Then we had this really weird cluster of 4 within 3 months. And then we haven't had a lot since then. So what do you do as sort of an economic and social issue? So we do monitor earthquakes throughout Kentucky. Most of the instruments are in the west. Some are traditional seismometers. Some are things called strong motion sensors, because if you were right near the epicenter of a big earthquake with a traditional seismometer, we just blow it off the scale. So you put in special instruments for very large earthquakes to measure the acceleration. And that's what's actually needed for structural engineering. We do have some in eastern Kentucky. Turns out there's a little cluster of events up near Ashland, Kentucky. There's something called the Eastern Tennessee Seismic Zone that sort of works its way in around this part of Kentucky. So we do have some earthquakes in Kentucky, and we monitor those using networking and real-time feedback. So if you're ever walking through a lobby, there are a couple of monitors, so you can see real-time scrolling of all the instruments. There's actually, you can jump up and down 2 or 3 from earthquake, because we have a instructional seismometer right there in the lobby. So sometimes that can be fun to do. We also do some microseismic monitoring. You probably all heard about shale and fracking, hydraulic fracturing, and unconventional resources. And in fact, at some places like Oklahoma, it's now made Oklahoma into the most earthquake-prone state in the country, far surpassing California. So we don't have yet any large-scale unconventional shale development in Kentucky, but we might. It turns out there's a potentially attractive shale, but it's very deep. Not much is known about it. It's called the Rogersville Shale. It's a Cambrian age that sort of runs through here to this band in eastern Kentucky. So what we've been doing for several years is doing microseismic monitoring. And the reason is, if there is ever a conventional oil and gas development there, it would be really, really nice to know what the background seismicity is. So you just don't start having earthquakes and you look back and say, well, gee, we don't know if this is anomalous or not, because we do have some natural earthquakes in Kentucky, and is this natural, and if it's not, and in any argument like that, if people have vested interest, they may pick one opinion or another. So what we've been doing is deploying an array of portable seismometers in places throughout eastern Kentucky for several years now, and just gathering background seismicity. And the good news is that there's essentially none. And we can pick up various earthquakes that you would never feel. We could be standing here talking, and there would be a swarm of them, and you would never feel. In some cases, down to almost magnitude 0, I think. Certainly down to magnitude 1. And you don't even feel it until it's by magnitude 3. It's a logarithm scale, so you're talking about tiny, tiny imperceptible earthquakes, but we've been monitoring those just to get background data. We've also done some background water quality monitoring as well. Landslides. We have landslides in a lot of parts of Kentucky. They cause millions of dollars of damage per year. Things like rock falls onto highways, landslides have to repair highways. Sometimes they involve homes. About the only good things, they typically are kind of fast-moving things that kill lots of people, like they can in areas like California or Washington. But we do have an active landslide program. We have a landslide database, and that's all available online. Now that we have airborne LiDAR coverage, we're doing a lot of really neat and innovative work, and I'll talk about that a little bit more later. China, you're talking about the visiting scholar from China. We almost consistently have between 2 and 4 Chinese visiting seismologists. One of the reasons we do that is because we don't often have really big earthquakes in Kentucky. We don't have a lot of data about what an earthquake would look like. And it turns out we think the kind of intraplate earthquakes we would have in Kentucky, say along the New Midway seismic zone, aren't quite the same as you would have along the plate margin, like the Pacific, where you have the standard greatest fault and it strikes slip movement, or the Cascadia subduction zone, where you have one tectonic plate being pushed under. Here in the Midwest, we have basically a continental rift that sort of stalled and failed long ago, so we're dealing with sort of stresses in a very ancient feature. So one of the things we can do is have access to a lot of Chinese data for intraplate earthquakes, do things like modeling of side effects here in Kentucky. So even though it seems like a tenuous correlation, like why in the world are we going to China to study earthquakes in Kentucky? It's because it gives us access to data that we wouldn't otherwise have. And it's very hard to get if you look for these collaborative arrangements. So we have the Chinese scholars come here. They went from us. We have one now who's actually working on implementing artificial intelligence algorithms in our microseismic monitoring network to pick up events that might otherwise go undetected. So that's turned out to be a very fruitful collaboration as well. Geologic data dissemination, almost all that's electronically. My predecessor, Jim Cobb, made the decision probably 20 years ago that everything KJHS has is going to be for free and not on the internet. So we spent a lot of time digitizing it. Some of our older and more obscure publications are digitized. Their policy is if you call and ask why you can't find this, we'll digitize it and put it on there. So our goal is to have every piece of information we have that's embedded and reviewed available on the internet. So we have a website, we have an interactive internet map server where you can go on there and turn on and off the geology. This is the faulted area in western Kentucky, the Rock Creek Fault System. You can plot locations of oil wells and gas wells, water wells, springs, sinkholes. You can put the geological formation. You can have physical information about the geological formation. We have thousands and thousands of water chemistry analyses. So you can just go up and down the menu and pick what you want to do and make your own maps. And then if you're really competent GIS user, you can download the underlying information, whether it's data tables or shape files or anything else from the web server. So we invest a lot of money in just disseminating geological information, and you can get it on your phone, which has been neat because actually I was in Representative Massey's office a while back in Washington talking about the utility of geology, and he was a bit skeptical about this, and I mentioned, well, you can look at all this new airborne LiDAR data and geological maps on your phone. He said, oh, really? What's the address? And he pulled out his phone and typed it in, and luckily it worked at his phone, so it was pretty embarrassing. But he was amazed that you can actually, you can pull up a geological map of Kentucky on your phone, basically, and do virtually everything you can on the website. We publish a lot of research. Traditionally, KJHS has had its own internal publication series, things like reports and investigations, but we also publish a lot in peer-reviewed journals because that's the gold standard of publication. We try to say, well, this is most of local, regional interest in Kentucky, and what elements might be of national or international interest, or finding data. And we say, okay, this is maybe a KJHS publication, and this was in a journal. And we try to balance those two. We have the well sample of the core library at CAR. You can see it looks like one of those Raiders of the Lost Ark kinds of warehouses. We have literally thousands and thousands and thousands of boxes of samples. It was just announced yesterday, it's really neat. We got a $250,000 grant that KJHS is going to match with another $250,000 from the Institute for Museum and Library Support, which is a federal program, to basically photograph 10,000 of these cores and put them all online. So it's going to be a 3-year, $500,000 effort to bring this core library, which now literally consists of boxes of rocks, into the digital age where you could sit in your office or sit at home and look these samples up and see what they are before you actually come out to examine them. And that's all publicly available. There's no charge for working with that. We have a Western Kentucky office in Henderson. It's always good to have a presence there. We do a lot of work with students who typically have 5 or 10 student employees. We do a lot of work with graduate students in various colleges. Analytical laboratories, we do a lot of water analysis. As I mentioned, we're working with mining engineering and CAER on rare earth projects. Recently obtained a transportable gas chromatograph and are just figuring out how to use that. So that would be really neat. It's not quite portable in the sense you can toss it in your day pack, but it's transportable in the sense you can put it in the back of a pickup truck and take it out, for example, to a well site to do some neat things. We just bought a couple of analytical grade radon detectors that are going to be very useful in our geohealth studies. And one of the things that I was particularly interested in, because a lot of my background has been in digital terrain modeling, both on land and when I was working in the oil industry in Houston, we were doing amazing stuff in 8 and 10 and 12,000 feet of water, complete darkness, and getting back ultra high resolution seismic and photographs from robotic submarines, and we do some amazing things with it. So one of the things that I did when I came to set up Digital Earth Analysis Lab, because as some of you don't know, how many people have worked with LiDAR data? You all know what LiDAR data is? LiDAR stands for light detection and ranging. It's a form of laser scanning, and one of the things you can do is put a LiDAR in an airplane and fly systematically over an area and create a laser scan of, in this case, the entire state of Kentucky. And that was just completed in the early part of this year, in January, so all the data finally became publicly available. So we have now a digital elevation model of the entire state of Kentucky with an elevation value every 5 feet. That comes to 460 million points. And if you actually look at the underlying data files that are the actual reflections of this laser bouncing back off of trees and houses and everything else, there are about 460 billion points of information. So we set up the Digital Earth Analysis Lab so we could work with this LiDAR and find useful applications for it. Things like geological mapping, sinkhole mapping. There's a lot of interest among foresters because we're interested in the ground and geomorphology. You all might be interested in the geomorphology that affects soils. Foresters might care about trees, so people use the tree cavity information for things like mapping of species. I've seen people using it for calculating fuel loads for wildfires. We use it to map very subtle geological features and things you can see if you're standing there on the ground. And the nice thing is, as well as this example shows, this is from Eastern Kentucky, you can computationally take out the trees. So in a really densely forested area, and I've used this in areas like equatorial jungles in Papua New Guinea, and you can just computationally take out the trees and see greater fair digital elevation model in an area where you couldn't before. So here's an example of an aerial photograph. You look at this and you see, there's a little some shade places here. But if you have the LiDAR coverage, you can see this area is just almost continuous sinkholes. And you would really see that in the photo. So those are the kinds of things we can do in terms of mapping sinkholes. We developed some workflows. We've done some deterministic things like this, where we actually look for those depressions and verify them. We've done some work in artificial intelligence and automated identification. But we basically increased our ability to identify sinkholes by a factor of 5. We identified 5 times as many sinkholes as we did before. This is LiDAR, actually from far western Kentucky, but this is the real fault scar, part of the limited seismic zone. Coming here, you can see how cleanly that stands out when we have this almost centimeter accurate elevation data for very large areas. We can map stream terraces, which has some very on soil formation. In this case, one of our mappers took the LiDAR digital elevation model and warped it to fit the gradient. In this case, the Licking River is also down the Ohio River, which lets us more easily identify things like fluvial terraces and custard terraces in these valleys, because we take out the gradient of the river, and that lets us more easily trace things like alluvial and fluvial and custard terraces. We use it for landslide mapping. This is a student intern we had last summer from Kent State University, working in the area around Prestonsburg, mapping landslides on this high-resolution LiDAR data, and then comparing it to the results of it's a probabilistic physics-based landslide hazard model. So we do things like that with it. Change detection. We have one LiDAR coverage for the whole state. Some areas are going to now start getting 2. And you can subtract those 2 coverages and look for things like landslides, which you can see up there. But there's also a lot of noise and some errors in the data sets. One of the things we're looking at are what are the limits of resolution of serial LiDAR data sets for change detection. And you can see if you do some cover filtering, you can actually get rid of a lot of noise and still see that there's a landslide right there. And also using LiDAR and older generations of coverage. So this is comparing LiDAR and the older national elevation data set from U.S. Geological Survey in an area where there's a lot of mountaintop removal mining to say, can we use this brand new technology and some older technology to get more exact footprints and volumes associated with mountaintop removal mining. And it does a pretty good job. I had to talk about this at a national meeting in November. There's some noise here, and it turns out a lot of this is due to errors in the older elevation data set. But you can see the areas where there truly was mining stand out really well. So we can actually, even in areas where we don't have 2 generations of LiDAR, compare it to older data sets if we understand the limits and the limits of resolution, limits of change detection. And then finally, we have postdoc working on a really neat project. There are about 14,000 known abandoned oil and gas wells in Kentucky, and there are who knows how many unknown abandoned wells. Gentlemen, people, if you properly abandon a well, you plug it, you cement it, and do all the right things. But often if you're abandoning a well, it might be because you're groping people money and doing it the right way, and especially if you're in 1830 or 1840 or 1850, you might not have been legally bound to do it the right way. There might be a lot more out there that we don't know about, and they could potentially pose environmental problems. So we have a postdoc at KJHS working with some of the people in computer science, trying to develop ways to use deep learning techniques to take this LiDAR data, given the locations of known oil and gas well installations, and find unknown abandoned oil and gas wells throughout Kentucky. So he's been working on that since about February or so. A lot of it, like a lot of problems, is just data management, figuring out how to handle when you have 460 billion points to work with, sort out what you need and get it in order. But we're making progress on that. And in this case, going from the DEM and looking at a sort of a visual hillshade image, a slope angle map. These things are called geomorphons. They're sort of a cruder level of machine learning and classification, and trying to put that through a convolutional neural network. And we're going to see if we can actually use that to identify abandoned oil and gas locations. And that should be the last slide. So if you have any questions, feel free to ask. I hope it was a good general introduction of what we do at KJHS.
Any questions for Bill?
I'm curious with your work with the underwater mapping and using what we hear in the news are all the risks with oil exploration 10,000 feet down. Can you give us some perspective from your perspective?
Yeah, there's always risk in that kind of endeavor. When you're doing 8,000 or 10,000 feet of water, it turns out right now 10,000 feet of water is about the practical limit because it has to do with the capacity of valves and pressures you have to deal with. In those low risk assessment project I worked on, and a lot of stuff I did was really phenomenal. So I'll tell you who was on the project, but I can't tell you for who or where it was.
Okay.
But it was for a series of 42-inch natural gas export routes that were going from like 9,000 feet of water up to an onshore to an LNG plant. And one of the questions was, okay, what happens if the pipeline ruptures? So you think of all the normal things like, there'll be an explosion, this was natural gas, so there would be oil leak. But one of the issues that came up was if the pipeline ruptures, the water pressure is going to be so great, the consequence the pipeline is going to be flooded by water. So you have to deal with things like that. There are huge underwater turbidity currents, underwater landslides that can travel tens of kilometers and move blocks almost the size of this building. And we can see that on our data. You can see a block, you can measure how big it is and say that, how many 100 or 1,000 cubic meters this block is. And then we see a track, like you got your fingernail down, except this track might be 20 or 30 or 40 kilometers long, going across the slope of maybe 3 or 4 degrees. So, yeah, technologically it's amazing. It's a little bit scary, but also the people I met there are probably some of the brightest people you would ever meet. And that was one of the amazing things about working in Houston, is that when you got people together in a room, these were people with PhDs from the best places on the planet, and they were some of the brightest people I ever saw. So, yeah, it's risky. There are potential problems. There are things like Deepwater Horizon, but when you look at what happened to that, apparently it was a bunch of stupid human decisions, not the technology. So yeah, there's a risk to everything we do. A lot of what my group did was try to take those geological things and say, well, is this a 1 in a million year event, or is it 1 in 1,000 year event? And we see these giant landslides. In a lot of cases, when we look at the dates of them, they were associated with the Pleistocene, the last ice age, when sea levels were much lower, and rivers would deliver sediment much farther out to sea. So those are conditions that don't exist anymore. We would try to take into account the possibility of a large earthquake and how that might trigger things. There was one project we worked on where we actually had some data, and we had some core samples taken in about 9,000 feet of water in carbon dates on either side of faults, and we could actually calculate probabilistically what the slip rates were, and we could tell the engineers what the likelihood there would be, the annual probability there would be, say, more than 5 centimeters of movement on that fault. So yeah, it is risky. You would be amazed if you saw the technology that's available, and the people working on it are incredibly bright, and they also realize that if something goes wrong, it's going to be a huge, it's kind of new to risk assessment, because you can look at financial consequences, you look at public relations consequences, you look at human health and safety consequences, so you look at all these things. And I was having a discussion with as part of one risk assessment, there was a whole group of people, and one of the things that came up was, well, okay, what was going to be your rate of natural gas moving through this pipeline, and what would the revenue be? It was going to be like $100 million a day. So that put everything in context in terms of human events where you might have a 1 in a million annual probability of occurrence, but would the consequences be acceptable, say, if they were just money and nobody was killed? So, yeah, there are risks, but it's not like those risks go unanalyzed. That the best companies know their risks, and they know it can be lost, and they really want it. And in a way, it's really refreshing, because you can imagine all the clients you deal with as a consultant. And if you're dealing with really, really sharp, technologically savvy consultants, or clients, sorry, that they're some of the best clients to work with because you can talk with them as professionals. Whereas if you're talking somebody who's trying to save money and cut costs in their corners, whereas these people do, and if you said, you know, you really need to know this, and they can say, okay, we'll go out and spend X millions of dollars to find the answer to this question. So there's no clear-cut answer, but it's not as scary as you might imagine, but nothing is without risk as well. And gas hydrants too. So you may have read about gas hydrants, which exist in a certain temperature pressure range in deep water near the seafloor, and they basically, if you warm them, they dissociate. So basically, the seafloor is frozen. So we did a lot of work with that as hatches as well, trying to figure out where those were, because if you destabilize those, the seafloor turns from something that's somewhat like permafrost to something that's like mush. That's another unique deep water hazard. Yeah, we're in the back corner.
Wait.
Yeah, Bill, I just wonder if KJHS has developed high resolution data of land use and cover change in Kentucky going back to early 1970s.
We don't have that. There are historical aerial photographs, and that's how they you could do that from, but we haven't done that specifically at KJHS. If
So
somebody did do it, I'd really like to have it, part of our data set, but no, we haven't done it at KJHS.
Okay, but I wonder, we have some photos showing land cover, land use, early stage, right? Great.
Do you have those photos or is
Yeah.
that Bill?
I would have to check to see exactly which photos they were. A lot of things we can get from the state GIS, from KJHS, those guys in Frankfurt, so they may have them, and often we just link to their server. So I don't know that we have them, but yeah, that's a good question.
Thanks.
So I saw that you had the groundwater monitors, and a lot of them are located in the eastern Kentucky coal fields. With the water crisis they had in Martin County, are these monitors monitoring any of the groundwater contaminants that are getting into the drinking water in the area? And if so, are those available in those publications you were speaking of?
We have a lot of water quality analyses. So if you go on our website, you can pick what analyte you want to look at and see what we have available from what locations and whether it's a well or a spring. The wells in the monitoring network right now are concerned primarily with water supply and water level. But with water quality, it's something good to do. We currently don't have funding for that. So I would say, if there's something in particular you're interested in, look at the data on our website. One of the things about water quality, especially in a lot of the areas in eastern Kentucky, the upwards are fractured bedrock, and that can be really tricky to characterize because most of the transport is through the fractures. There's little transport between the matrix and the rocks. So you could have a monitoring well, and you could have a pool of contaminants almost within sight, but you wouldn't pick that up because the contamination might be pulling down one fault zone or one fault system, and your well might, if you're unfortunate, it might be in the matrix. You didn't intersect any fractures, and it wasn't a very good well, or it might intersect some fractures, but fractures that for one reason or another are connected to the ones carrying the contaminants. So contaminant hydrogeology and fractured rocks can be a really hairy proposition because you would have to be right on, and you've got fluid going past you. So it's an issue, and I would say if they were a particular, say, residential well or municipal well where it was concerned, you would pretty much have to go to that well and sample it because you could have a monitoring well nearby that may or may not reflect what's going on in the actual water supply well.
Any others?